How about now? Did I accidentally turn that off? Uh, yeah. Well, that explains. Yeah, last night I was trying to. I tried. Oh my god, several times to record a reaction video to. There's a video by D Bios YouTuber, and I was reacting to his video, and then um um yeah, I tried recording several times, and I realized the audio wasn't working each time. Oh yeah. Anyways, Leo, do you remember this thing? I made this claim. I meant to say h lower 2 of this shape is z4. You know, and maybe I'm wrong, but maybe I'm wrong, but reacts don't need audio. Yeah. Yeah, how does it go? How does it go? It's intersection to sum to x. Right. Also false? Okay. Well, let's plug in Meyer via Torus and see what happens. Um, so what do we got? We'll have 0, we'll have h 0 x. Well, we already know what that's going to be. We're looking at this glue, these tubes over here. We'll have z, we'll have and what am I going to do? The top part, like one of these parts will be the blue and above, and then the other one will be is there a nice I want a nice purple. Is that what I want? Nah. Okay, how long am I gonna screw around with colors for? I don't know. Right, so there'll be the top part, uh, and then we'll take this other part here. Brute force this with simplicial, yeah, yeah. That's what I thought about first, but let me Meyer via Torus this. So each of those two things are going to be connected things. So we'll have a z, some z, and then we'll have an h naught of the intersection, and the intersection is just 4 tubes, so this should be a z4. And then that should come from a term over here. So now this is h1 of our shape. Then we have, what is this? It's going to be h1 of the two shapes, which is trivial. Then we're going to have h1 of the sum, which is a bunch of, h1 of the intersection. There's h1 of a bunch of tubes, so that's 4 z4s. And then here we have an h2 of x. And then here we have the sum of h2s, which, maybe here's where I made the mistake. No, the h2s should be trivial, right? This should be 0 because um well, wait a second. Oh wait, the h1s aren't trivial either. Slow my roll. Um Slow my roll. Let's think here. No, they are. They are. They are. No. Oh Lord. Okay, let's see. Cause what do we have? Cause it's a 2B boy. We got a little 2B boy like this. Right? This is each of our things is a 2B boy. Right. I lied. Yeah, so definitely H1 is not trivial. Good morning, Guitar Freak. Right, H1 is definitely not trivial. Uh-huh. Okay, what's the best way to do? Okay, so I completely lied then. And maybe H2 isn't trivial as well. Okay, so maybe we do just want to brute force maybe we do just want to brute force this. Each half has the homotopy type of a bouquet of 4 spheres. Of 4 spheres, right? I'm trying to see this. Wow, a rod bullied you for 4 hours straight. That's incredible. And you lived to tell the tale. Why am I'm just having trouble picture this. Four circles, you know. Why is that the case though? Because I mean, each of these circles, yeah. I guess we could flatten it out to be this, right? We can flatten it out to be this. Because this outside hole becomes the inside, and so you flatten it out like this, and then you contract it. Isn't it 3 circles? Because then we could contract it to this, right? Like imagine taking this say this circle here becomes the outside boundary, and then you contract it down to the circle. So I think it should be 3 circles, no? Yeah. But how does that help us with computing? Oh, I guess that does tell us that H1 is what's the wedge of circles? So is it the sun? Is it Z3? But if 4 is 3, it is 4. You can't be saying stuff like that in chat. You're gonna break my brain. Right. I don't even remember. Why am I confused? Is it? Yeah, it is direct sum. Okay. Homology of wedges, just direct sum. I was worried for a second that we were taking a free product, but homology of wedge is sum of homologies in all dimensions. Is that true? I don't know if that's true. Is that true? So anyways, I guess we should have 2 Z3s here. So really, I guess we should have a Z6. Here we should have a Z6. And then here we should have Z4. For one for each of our 4 tubes. And then, yeah, so I was probably wrong about my H2. Then we have H2. Then we have H2. Then we have the H2s of again this thing. But this should have trivial H2s, right? Yeah, 100% that is trivial H2s. So this should be 0. And the intersection should have trivial H2s. Yeah. Reduced homology pukes. Homology of pairs. Amazing, beautiful for some reason. Okay. Right, so I see. So, I mean, H2 does inject. H2 does inject. Reduced homology. Yeah. So I wonder, can we actually just can we get H1 from pi 1? Is that maybe the way to go? I mean, just looking at it. Yeah, basically it is a 3-hold. Well, it's a 3-hold torus. Right, so shouldn't it be like 3 Z's starred together? No, one whole torus is 2 Z's. So it should be 4 Z's. And then if we take the abelianization, does that just give us Z4? Am I crazy? Yeah, I can't even tell if you guys are yapping in chat. What? Small group tour? Thanks. H1 of 3-hold torus. Let me just fact check myself here real quick. Z6? What did I do wrong? Burr went to pi 1 because H1 was too hard, apparently. Yeah, why is it? Shouldn't we have? Why is it Z6? I mean, now that I see the 2G formula, that makes sense. But then why? How did I get this wrong? What does Wolfram say? The genus of a complex torus is half the dimension of H1. Yeah. Yeah, I should just make some complex and then compute it. We could also... Is it worth Van Kampening this? Probably not. It's become a bakery in a lovely hamlet in some small town upstate. It is the season for doing that. It is, Christmas Hallmark season. Am I computing for a genus 3 surface or a torus with holes? Uh, well, for H1X, is a genus 3 surface. H1X is a genus 3 surface. I mean, if it is Z6, then we should be done, right? Because we can just determine that, wait, there's no way that H1, no. H1 is not Z6. Come on. Am I out of my mind? H1 is not Z6. Is it? If it is, somehow I feel like that's not right, but maybe I'm crazy. If it is, then we should have the alternating sum. If I did everything else right, this should all be 0. Genus G surfaces. Yeah, I guess it is. I don't know why this seems weird to. When I thought about it the other day, I convinced myself that wasn't the case. But so these cancel out. We get -1. Okay, so H2x. H2x is dimension 1 then. Right. H2x is Z. So I was wrong. Think about it as connected sum of 3 ordinary tori. Right. Each torus contributes 2 generators. And they might get mixed up in pi 1, but that doesn't concern H1. Right. The lion H1 isn't concerned with the generators of pi 1. Groups can have genus. Source, you made it up. Well, there you go. Okay. Nice. Now, how would we set up what's the best way to set up the complex to compute it if we were to just do brute force combinatorics? Like in this picture here. I'm tempted to even crack open Hatcher and try and think about it. I mean, what's the complex for just an ordinary torus? What do we do? Can we have like a single loop like this? Can we have a single loop as such, and then we have another loop? Yeah, what am I trying to say here? How do we even just set up let's say an ordinary tube? Yeah. Can we do something like this? Got into a fight with half of tau and a bunch of homotopy theorists in pi 1. Yeah, I do feel like there's some joke hiding there, but by gluing opposite faces of a square, yeah. Oh yeah, I guess we could. Right, I guess the way to, I guess, right. What's the way? There's the folding. Right. So, what's the way to do it? Is the genus 3 surface. So a torus is a folded square. A double torus, you can give the instructions for gluing as a what is it, an octagon? Is it an octagon? Or is it? No, it's six-sided. Because shouldn't it it should correspond to gluing two of these along an edge, right? And then so this should be six-sided, and then the octagon should be the three-hole torus, right? The octagon should be the three-hole torus. If you found a complex structure on S1, you'd be impressed. What? Guitar Freak, I'm trying to just redo this computation. Oh yeah, Locke already said in chat. Yeah, it's eight-sided. Right. So, and let me see. Let's see. The gluing of the torus. So the torus is, we have an arrow, two arrows. All the arrows point in the same direction. Is that right? Yes. Okay. So now I'm going to glue it together in pieces. So let's see. So this is going to be what? So let's call this A, B, A inverse, B inverse, right? And then I'll also have a C, D, C inverse, D inverse, and E, F, E inverse, F inverse. I'm going to glue these together one by one. You have 4 generators for genus 2. And there will always be 2 sides identified for each generator. Yeah. Now, what do I do? I could set... Just compute atalco homology and compare to Betty afterwards. Well, maybe we can try doing that next. Maybe we could try doing that next. Yeah. Atalco homology, yeah, with respect to the analytics site for this thing. I mean, we could. Came across a post on a popular science Facebook page. Walks in rotation space return home when doubled and scaled. Well, maybe I'll take a look. Walks in rotation space. You can't glue edges to edges with these tori to get there? What? Can I not? Can I not? I mean, doesn't the direct sum of a tori just correspond to gluing 2 edges together? Am I wrong about that? Yeah, if I tube it up like this, if I make an elongated version like this, yeah, what am I saying? I should probably just look up the if you picture what that would do, it's quite wrong. Okay. I should probably just look up the gluing instructions then. Gluing one edge to another is like taking 2 radial circles. Okay, sure. Hatcher has the general delta structure. Yeah. I guess I should do this. Why am I even doing this? What's the point of me even doing this? Why do I even do anything? Okay, I'm trying to... Why would I bother trying to drive this live on stream? I don't know. What's wrong with me? Yeah, I don't know. God, I'll just look it up. Yeah, let's look at this other paper. Maybe I'll come back to that. I should probably be working on how to get my focaccia to be more savory. And think about the layout of the cafe in front. I think I'm pretty happy with my focaccia, to be honest. Should I think about the layout of the cafe in front? Yeah, probably. But I think I'm happy with where my focaccia making skills are at. Actually, I haven't made any for a while. I should probably make some. Okay, the dynamics of numerous physical systems, such as spins, qubits, can be described as a series of rotation operations, i.e., walks in the manifold of the rotation group. A basic question with practical applications is how likely and under what conditions such walks return to the origin, which means that the physical system returns to its initial state. In 3 dimensions, we show that almost every walk in SO3 or SO2, even a very complicated one, will preferentially return to the origin simply by traversing the walk twice in a row and uniformly scaling all rotation angles. Crazy. Crazy. Also, infinity category theory update. You managed to code up the interface infinity category theory? Huh? How did you do that? And what do you mean by that exactly? You just have no examples of infinity categories that don't take infinite RAM. What is the distribution of walks here? Well, I guess we'll find out in a second. Rotations are omnipresent in physics, governing the dynamics of dipole spins, qubits, Lorentz transformations, blah, blah, blah. A spin evolving in a time-dependent magnetic field, BT. The motion of a spin state is a succession of infinitesimal rotations, each around the instantaneous. Blah, blah, blah. Okay. Almost always possible. Okay, will be explained shortly. All we need to apply the sequence twice and then uniformly do something. Where's the math? A rod has infinite RAM and is about to boom your ass. Yeah, well, a rod's not a computer. Well, actually, as far as a rod might be a computer. I've never seen a rod in the flesh. I've never seen a rod on camera. And even then, how do I know it's not AI deepfake? Yeah. So random walk on SO3, shown as a trajectory in a ball of radius pi. Okay. Is mapped to the point. We map a walk to a point. Your research has a lot of physics in it. Oh, right. Because something quantum algebra. There was something about when I was looking at your paper yesterday. I remember seeing something quantum algebra. Their naming conventions, fair. Yeah. Visualize 3D rotations as points inside a ball of radius pi with antipodal points identified. Right. So RP3, by mapping each rotation to the point, I see. We're mapping the rotation Rn. Wait, what does n mean? Ah, I shouldn't have skipped all the definitions. Rn omega? What is Rn omega? 10? Yeah, wait. Is this notation not defined? Why don't you define your notation in the paper? Okay, R is in SOD. Oh, N is the axis. I see. N is the axis and omega is the angle. Okay. Okay. N is the axis. I see. So you send it to the axis, the point, which is the axis times the angle. I'm still kind of confused here. Ball of radiant, yeah. Found a cute proof that F star is cyclic for a finite field last night. Might post a 5-minute video on it. You should do it. Why would we define notation? Yeah, who cares? Yes. But then, how is n times omega a point in here? I don't know. You thought RP3 was a quotient of S2? No. RP3 is projective 3 space. RP2 would be the quotient of S2. Right? Yeah, wait a second. RP2 is a quotient of S2. Okay, well, I need to go. I need to go. I got somewhere to be for 10, and it takes me time to get places. So we accomplished very little today, but that's okay. QED.